Hi everyone. I have to, you know I do. Welcome to the lecture. So this is actually more meta than it looks like with this meme. Because remember yesterday I asked if anyone's got an AI meme? So this isn't just asking AI for a meme, this is asking the class for a meme, and this is what it gives me. So I thought that was quite cool. Thanks to the person who sent it, by the way. I did rather enjoy it. Yes? Anyone else want to explain?
In a little town called Scranton, there was a pizza selling business, and then it was the manager.
Yeah.
And that was the old manager, and that was, I think, the transfer or his first day.
Still don't get why it's funny. It's one of those that it's so not funny that it's funny.
I think it's because who is the AI in this picture? Who's uncertain? Are you the person congratulating the AI who really doesn't know what he's doing? Or are you the person giving over to the AI?
Who's the Marcus class? Is it you or is it AI?
I don't know. Anyway, thanks very much for the person who sent it. Everyone seems to have enjoyed it, if not understood it. All right. So, welcome to the lecture. Yesterday we chatted mainly about genetic algorithms and other evolutionary computation type things. And we spoke about the different operators, and I've already had a couple of questions about people who've tried implementing the prac. Yay, that's good. What I want to quickly just speak about today are sort of two things. The one is a thing that deals with genetic algorithms, and it's called the schema theorem. Theorem. Now, this is not a theorem. But it is an explanation of why genetic algorithms work. And so the idea is, if you've got a representation of something, okay, then you can create schemata, all right, which is the plural, which are then templates that we essentially go and say, so this block has a certain value, this block has a certain value, that block has a certain value, and what the heck, let's say this region has a certain value. And what happens is the schema theorem then basically argues that if you run this through a genetic algorithm process, then schemata, if this pattern corresponds to a good fitness value, to a good objective function value, same thing, then it's more likely to survive to the next generation of a genetic algorithm than if it has a bad fitness function. Okay, so that's essentially the argument behind it. There's a bit more behind that. It's not a theorem. It's not a proof that genetic algorithms will combine, but it does at least give some sort of warm, fuzzy feeling that genetic algorithms should work. More than that, it doesn't really do much. So, there's a quote in the previous version of the textbook, I hope it's still in the current version, but it says, "At present, it is not clear whether the appeal of genetic algorithms arises from their performance or from their aesthetically pleasing origins in the theory of evolution." Which is a nice way of saying, they're cool, but are they really? Okay, so that is an absolutely fair comment. There is no proof that genetic algorithms will converge. There's no proof that they're any way better than anything else. They just do tend to work at all, which is often what we're looking for. Remember here, we're not worried about how we get the solution, we're worried about the solution we end up with. And if you can dream up mutation, crossover, representation, fitness, and selection for a particular problem, you can apply a genetic algorithm type approach to it. So as I say, as one algorithm we're going to consider in a bit of detail, it's a good one to consider, but be aware that there's no mathematical proof or anything that says that it's going to be better. Now we get to the one I absolutely love, and this is completely seriously, this is the name of it, and it is the no free lunch theorem. I am not joking. If you go and look at this, you will find at 3 papers, 2 of them with a derivation by the original people that dreamt it up, and then one by a person who gave them some comments in addition to it. And what this theorem actually says is that there is no universal optimization algorithm. It does not exist. And that this one we can prove mathematically. Mathematically provably, if you have an algorithm that works well on one type of problem, it must work badly on another type of problem. So be aware that while I say genetic algorithm is a nice thing to carry around with you, it is provable that if it works well on a certain problem, and it does seem to work well on a number of types of problem, it must work badly on other problems. So please keep this in mind. This is not something that's in the textbook. I just love telling people there's a no free lunch theorem. But also it is an important principle. I mean, it comes back to that sort of argument of using a hammer on a screw doesn't work very well. Using a screwdriver on a screw works brilliantly. So use the right tool for the task at hand. Genetic algorithms are often not the best tool, but they're often not the worst tools. They're sort of the monkey wrench, the shifting spanner of tools. You can use it in a lot of places, but you can't use it everywhere. The other thing I just want to bring up is we're going to speak a bit now about local optimizers. And in the spirit of, if there's one thing you should know about, I think this should be it. There is quite an old algorithm. It predates me by like a decade, so it's, if you think I'm old. And it's the Nelder-Mead. I can't remember if there's an E on the end of Mead. I feel like there should be. Just put a little question mark there. So it's the Nelder-Mead local optimization algorithm. It's a gradient-free optimizer. There was a professor here who taught the beautifully named optimization course, Moo 780. The fun the mechanical engineers have. And I asked him once and said, I'm using Nelder-Mead for this problem. Should I use a better algorithm? He says, unless there's a very good reason not to, in terms of local optimizers. So this is sort of local hill climbing algorithm. So we've got a good starting point, and we want to get to the best solution near it. You can do a lot worse than Nelder-Mead. It's trivially simple to implement, and the vast majority of the time it works. Yes, there are mathematical proofs that show that there are problems where it doesn't work. Yes, there are algorithms that do work better. They'll take less function evaluations in order to get you the better solution. But if there's one name that you need to know for a local optimizer, you can do a lot worse than using this thing. Okay, so it's as I say, it's just one of those handy things to keep in mind. Simple to implement, actually works the vast majority of the time. Can you do better? Yes. But the time and energy you're going to have to expend to do better, unless you've got a library hanging around, is quite significant. So it's a handy thing to just keep in mind. All right. Now, I mentioned that most of the state-of-the-art algorithms for, let's call it global optimization, I'm going to call it population. Well, most of the state-of-the-art algorithms for global optimizations, this isn't where we're just trying to find the best solution near our starting point and we want to get there as quickly as possible. So not a greedy hill climbing type algorithm, but something that considers the solution space. They're all population based nowadays. Algorithms. And to try to make an exhaustive list of these things will keep us busy for days. Because these things, there are just so many of these things. The one I do want to mention is particle swarm optimization, often abbreviated PSO. This is a thing that's designed to mimic how birds flock effectively. It's a very simple mathematical model. Again, it's a nice global optimizer. The benefit of this thing is it's actually built for continuous variables. So genetic algorithms, at least in their traditional form, are binary. Yes, we can change them, but this algorithm is actually built for that specific case. It also gets used a heck of a lot. The difference here is the way the collaboration between the various particles work, but it is another widely used one. Another one that I've seen quite a bit, but which I'm still not entirely sure I understand why it works so well, is ant colony optimization. Is that correct? Why does it look wrong? That's right. Is ant colony optimization, sometimes abbreviated ACO. And then we start throwing names out there. So pseudo-binary inference learning, I think is what it stands for. It's what happens to a genetic algorithm if you take the population away. Then there's differential evolution, which looks at the differences between solutions and updates things on that. And then we get into the weird stuff. So we have the grey wolf algorithm. We have the whale song algorithm. We have the firefly algorithm. And my personal favorite, the cat swarm algorithm. So these things tend to get really weird. Oh, there's also the bees algorithm. Not BS, bees. Which I've had some success playing with over time. There are so many of these things now, it's just absolutely ridiculous. And if you go and break them down, there are actually very, very few unique ideas in these things. So the grey wolf algorithm is kind of a spin on particle swarm optimization. So why do we need to have this completely separate thing? And then people go and make the improved grey wolf algorithm. Yeah, it gets rather silly, but the ones I can say that the genetic algorithm and particle swarm optimization I know work well. I can with some confidence say that these are good things to look at. But the main point I'm trying to make here is that all of these algorithms are population based. Yes, I know I said this one is what happens to a GA if you take away the population. Essentially what you do is you create a population, analyze it, make one solution. Create a population, but there's still a population in there even though they don't admit it. So there are lots of these things. If you ever start looking in the literature and you start running into a million of these things, stop. You could literally keep yourself busy for the rest of this year just investigating these things. It's got quite silly. Question?
From the PPIR,
yes.
Banks population said one solution, wouldn't that favor what we're talking about?
Yes, so you're losing diversity, except the single thing it creates is a bunch of probabilities, not a single value. So yeah, the point is you need to go and dig into all the details of these, and each one has a slightly different variation on the same theme. They're more similar than they are different. We're essentially trying to use a number of different things in order to create a better solution. So for example, particle swarm optimization, we have particles which are flying through an n-dimensional space. They've got momentum and velocity, so they tend to keep going in the same direction, except that the best solution so far has a spring attached to each particle, pulling it to that, and each particle keeps track of its own best solution that it's found. It's got a spring pulling it back there. Sounds like it shouldn't work. It does, surprisingly well. Kind of like genetic algorithms. Sounds like it shouldn't work. It does, surprisingly well. They're all different varieties of how we get solutions to work together. Main point is population-based algorithms are where there's a lot of stuff happening at the moment in these global things. Local optimization, typically Nelda Mead is your friend, but there are more advanced algorithms. Okay, so that's what I wanted to say about those things. Now, the textbook has like 2 pages on what I like to think of as traditional mathematical optimization. This is where we start with a solution and we want to get to the best solution close to it as quickly and as efficiently as possible. Work on this has been done since at least the 1960s. Well, probably earlier because that's when Nelda Mead was published. So this is a very mature, very old field, and the textbook gives it 2 pages. I understand there's a lot to consider in AI, but I would argue that a lot of what people look at as AI is actually optimization algorithms. So one of the primary breakthroughs in neural networks was the backpropagation algorithm. Backpropagation is a combination of 2 things. Steepest descent, the worst possible gradient-based optimizer you can get, and a very efficient way of computing the gradients. That's actually where the interesting thing lies. But you don't have to use the worst. Why do you phone me when I'm in a lecture? I do not want your robot bank spam. All right. Yeah. What was I saying? And there are a lot of things where, oh look, there's this weirdly shaped piece of metal and it's lighter and stronger than the thing before. I think that's just a mathematical optimizer that they've applied to it. So I really think that mathematical optimization is, a lot of the time when people say this is AI, they actually mean it's mathematical optimization. So just keep that in mind. It's an incredibly powerful tool. Pretty much any software package that you have that has a simulator nowadays also includes a bunch of optimizers. And so if you give it the starting thing, tell it to optimize, great, it produces something amazing. Is that intelligent? No, it's a piece of applied maths, but it looks intelligent, weak AI hypothesis. And I just think a lot of what people call AI is actually local optimization. So I'm just going to call this local optimization for now. All right. So with a mathematical one, we're not dealing with discrete states. We're now dealing with continuous variables. So this is typically where you've got size, space, position of something, no, I'm missing a U, continuous variables. All right, so this is what constrains our state space. So we're dealing more with the factored representation. Remember, we have a bunch of parameters that define the state that we're in rather than discrete states, which we've been considering up until now. We can discretize these things, and some of the algorithms actually do that, but typically we consider them as continuous variables. The next important thing is the vast majority of the stuff that comes from the mathematicians, which is typically the really efficient stuff, needs the gradient of the objective function. So it needs the gradient of the objective value. Because the gradient tells us which way to go to get the fastest increase or the fastest change. So that is actually really important. It can have a huge effect on accelerating convergence because it's extra information about the problem. However, we don't always have gradient information. If we're performing a simulation, we often don't have the gradient of this simulation outcome to this parameter which you want to vary. So if we've got a mathematical model, yes, we can normally work out the gradients. So the problem with these things is a lot of the time is we don't have the gradient information, and so we can't apply many of the most advanced algorithms. So we've either got two choices, basically resort to Nel-de-Meade, and I've tried some more advanced modern algorithms. They give about the same performance. So it's either resort to something like Nel-de-Meade, which doesn't use gradients, or estimate the gradients. And estimating the gradients is, if we've got a point over there in a two-dimensional space, then we take a step that direction, we can work the gradient, or we can estimate the gradient in that direction, take a step in that direction, and we can estimate the gradient in that direction. Because if you've got 2 points, you can approximate the gradient. Simple, except how far apart should those 2 points be? Sounds like a simple problem. It's not. In the mathematical case, you've got rounding errors that crop up. If you've got a simulation, you've got inherent errors in a simulation. So you can't make that step too small because otherwise your gradient is now dominated by these mathematical artifacts. But you can't make it too big, otherwise it's not an accurate reflection of the gradient. So that's not great. Then we also get to the problem, so let's just say we can evaluate it numerically. We also get to the problem that if you've got a 100-dimensional space, then you need one computation to work out the value for where you are at the moment, and another 100 to work the gradient out. So it can often be better just use an algorithm without gradient approximations and you'll do better. My very limited experience, I haven't tried this out much, is that normally numerically estimating the gradient seems to get better results, but don't quote me on that. I've just recorded it, that was silly. So even if you have to numerically estimate the gradients, it's not necessarily a bad thing. Just be aware that there are some gotchas in there. The other thing is automatic differentiation tools. These are increasingly becoming available. I gather Julia, the programming language, has an automatic differentiation function just built in. So if you give a function and say, the objective function value for this thing is this, it will give you code that then computes the gradient. And there are actually ways of doing that from source code. So we nowadays have access to this kind of automatic differentiation tool, which means we don't need to make a numerical estimate, which helps a lot. So even if you can't mathematically determine the gradient, there are many cases where one can just use automatic differentiation tools or things like that. Years ago, I saw in microwave theory of all places, they were looking at determining the gradient of a circuit's response parameter to every component in the circuit. It's basically take the circuit, modify it in this way, simulate that circuit, and the gradient comes out. I don't know. Smarter people than me. So there are often tricks that our gradient information is so important that people have often come up with very clever ways to determine the gradient, which is kind of an indication of how important these algorithms are. If people are prepared to go to such lengths to get gradients, you better believe those gradients are important. So that's worth keeping in mind. I spoke about the step size. So I've spoken about the step size here. We also have a step size in terms of the algorithm as a whole. So the question is, well, remember, simulated annealing, sorry, I'm getting old. In simulated annealing, we initially allow big step sizes because we're searching the problem, right? And later on we reduce it. That seems like it might be a good idea. The only problem is many of these algorithms build up an estimate of what the problem space looks like. Typically a quadratic estimate. Why? Quadratic is the smallest non-linear function that you can get. So basically whatever your thing looks like, I'm fitting a quadratic to it. And it works surprisingly well. So don't think I'm mocking it. It actually works really well. But that quadratic estimate is only valid a certain distance away from the current point. So we need to be careful in terms of taking step sizes. We want to allow big step sizes so that we can get to the solution quickly. But if we allow step sizes that are too big, we get out of the region in which our model is accurate and we end up chasing our tail. And there's actually a whole class of algorithms which are called trust region methods. Trust region methods. And what these effectively do is say, try to find ways to adaptively adjust your step size based on how accurate the model has proved to be. So if you're taking very, very small step size and you're finding, man, this model is perfectly accurate, well then take a bigger step size. And you keep doing that until the model's accuracy starts dropping, then you reduce the step size. And that's very simplistically what trust region algorithms do. So that's kind of the idea behind that. The other thing we can do is say, well, if we've got a two-dimensional space and we've got contours like this, so this is either a valley or a hill, depending on how you look at it. All right. What we can do is say, well, if we're over here, let's use another color. If we're over there, the gradient tells us we need to go in that direction. How far do we need to go? This is what we're speaking about. So with the trust region method, we can say we'll start off assuming that our model's only accurate and take small steps until we get confidence in our model, and then adjust that adaptively. The other one we can do is say, well, let's take the objective function value along that line. So let's call this direction just our x. So that's 0, and then that's some value. And this is then our objective function value. That's going to look something like that. All right, if we just move along that line. So what we can also do is do a line search. And the line search says we actually only adjust one variable, which is the distance along this line, and we find the minimum along that line. And line searches form an integral part of many, many optimization algorithms. One of the key reasons for that is your final solution takes you down to where the gradient is 0. So it takes you down to where that estimate is at its lowest value. And based on the fact that you now know where that point is, you can do clever things with the models. All right. And for example, in Newton's method, you get, Davidson, Fletcher, Powell, Broyden, Fletcher, Goldfarb, Shano. These are the names of the people that dreamt these pieces of matrix murder up. And effectively what they do is they use this fact that you know where the gradient is 0 in order to build up your two-dimensional Hessian matrix, which is your second derivatives matrix. If you actually sit and think about it a bit, the work these folks have done is freaking amazing. But that's then a line search. So a line search-based optimizer is a very, very common approach for these reasons. And that also allows us then to have an adaptive step size. Nelda Mead, okay. I see I've got a note for Nelda Mead, and it's Nelda, I was wrong, Mead, no E. I'm so sorry. All right, so you create a simplex. So if you've got a 100-dimensional space, you create 101 points. And then it's got rules based on how the solutions at those various points compare in how you select the next point. And the idea is when we've got a valley like this set of points gradually goes and squeezes itself down and along the valley and then gradually converges like that. This is a comparatively simple problem. There's a very well-known standard test problem whose okay, this is really badly drawn, but the contour map looks something like that. So the point is, if you start off over here, you need to go down there, and the model has to completely change as you go around that circle. Rosenbrock's test problem. And so what Nelda Mead does is essentially tries to get its little simplex in here And then when it hits that point, it makes the simplex smaller until it can get round, and then when it can, it extends it again. That's what they try to do. The way they do it is really, really simple. Again, I've said why it's a good idea. It's generally reliable. That button, not the other one. All right. Then, the one that I have been maligning this whole semester is steepest descent. Let me tell you why it is so horrible. All right, so let's go back to our comparatively simple diagram. So we've got this thing. So steepest descent says we start, let's start further from the middle. We start there, okay? And all we do is we say, pick the direction with the fastest gradient. So either decreasing, or the direction that it's going the fastest down if we want to minimize, or up if we want to maximize. And then in the normal form, do a line search along it, find the minimum. That sounds like a really good approach, doesn't it? Because you just go down that thing, you're already at the bottom of that dip. Now comes the problem. You're just over the side of that dip, and steepest descent then goes. Sorry, let's try that again. It then goes like this. And the problem is it never actually goes along the thing, because every time you do an optimization in one direction, you go slightly beyond, you go to where the zero is along that line, but then when you get to that point and look at the overall problem, it's basically straight back in the opposite direction as a whole. So this is the problem with steepest descent. It really doesn't do well in long, narrow valleys. It's actually pretty terrible there. So steepest descent sounds like a good idea. We're using the gradient information, we're using line searches, we're going in the right direction. Surely this will be brilliant. Yeah, not really. It does work, but it's really not very efficient. What we'd rather have is something that goes, that way. We go from here to there to there. And that's what we're actually looking for. And there are far more complex algorithms that do this. Okay, but their complexity is justified because instead of having to take 100 steps, we can potentially take as few as 2, which I think is pretty amazing. So steepest descent seems like a good idea. It's not. There is another variation of steepest descent where we don't say that we do a line search. So instead of spending the time doing line searches, we just say we've got a fixed step size. And now we have a problem. What if our step size is too big? Well, if our step size is too big, we're going to go from there to there, from there to there, and we're going to do this. And then when we get to the solution, we're just going to start jumping around it the whole time and never get to the solution. So the problem is if we have a non-adaptive step size and it's too big, we end up not actually ever reaching the solution. If we have a non-adaptive size that is too small, then we do this. You can see the problem. If your step size is too small, you take forever to converge. If your step size is too big, you never converge. So if you really need a solution, small step size is probably preferable because a large solution is never going to actually converge. But if you just want to get close to a solution, a large step size might be better. Again, there's a lot of complexity in even the simple sounding things. The other way is just make the step size smaller as time goes by. Same idea as simulated annealing again, and hey, guess what? It works, and guess what? Even better, it's exactly what they do in neural networks. When you learn about backpropagation, it's exactly what they do there. All right. So then we get to sort of the Newton methods, or quasi-Newton methods. Let me rather say that. This is a whole class of algorithms on their own, quasi-Newton. So these things form a quadratic, but a matrix quadratic estimate of the problem. So it's a quadratic fit. Have you guys done Newton's method? Okay, so the idea is if you're at a point and you know the gradient, you can take a single step and get to the solution. If you have an n-dimensional problem, Newton's method says you can take n steps and end up at the solution. If you've got a 100-dimensional problem, you can take 100 steps and you'll get to the perfect solution if it's a quadratic problem. All right. So here you can see this problem of what this assumption looks like, what that quadratic model looks like. But it has what they call quadratic convergence, because for a quadratic problem, it only takes the same number of steps as you have dimensions in the problem. So it effectively searches along each variable once, but it does it in kind of a clever way so that you don't get either of these situations. You get the there, there, because this is a two-dimensional problem. If it's a perfect quadratic problem, it gets there in 2 steps. If it's not a perfect quadratic problem, it still does pretty darn well. The problem with these things is, I'm not saying it. The problem with these things is that you're effectively relying on inverting the Hessian matrix. So what they do is they don't form an estimate of the Hessian matrix. Actually, let me just write this. So we're making the estimate that our objective function value is approximately equal to x times a times x transpose plus b transpose times x plus c. That's an n by n matrix. This is a 1 by n matrix, and this is a constant. So it's a full matrix thing, but it's quadratic because that's a quadratic term, and that's the highest approximation we're using. So in other techniques like conjugate gradient, we create an estimate of that Hessian matrix that they call it. In this thing, we form an estimate of the inverse of the Hessian matrix. Anyway, that's the idea. The ones that seem to get used a lot more are the conjugate gradient techniques. Conjugate gradient techniques. So they use a similar estimate, but they do it in a slightly different way. And I just see them used a lot more than the quasi-Newton methods. So again, they form a quadratic assumption. It's just the way they use that quadratic information is different. They also have that quadratic convergence. So if you have 100 variables, they take 100 steps to converge if it's a quadratic problem. Sorry, I forgot you had a question.
Sorry. For the deepest, the one we did previously, the big problem you can run into is if it has large step sizes, it will just keep going. Once it gets close to the solution, it will keep going over and it won't necessarily be able to get there.
Yeah.
What if you had the step size decrement, or not decrement, would decrease according to some function every time it goes past the goal? Would that be possible?
Then you're starting to move into trust region type methods because you're saying how far do we trust this model, and the model includes our step size. So you can potentially have a trust region model or just gradually decrease the step size as time goes by. Because as time goes by, we should be closer to the solution, so a smaller step size will help us converge.
Would it not be more reliable to decrease the step size as we get closer to the solution rather than as time decreases?
How do you know you're close to the solution? I know that sounds like a silly question, but that is actually a major question, because we can have a very large region of an approximately zero gradient. So you think you're close to the solution, but you're actually not. Basically, there's a reason. There are entire journals devoted, journals, not one, journals devoted to this kind of thing. It's very seldom as simple as one thinks, unfortunately. And if you have a really good idea, there's some journals you can publish in. This kind of thing it's an important problem. People use them for everything. It is really, this is important. This quadratic assumption is the assumption most mathematical techniques use. The one problem with this is if we have something like a filter response, so if this is frequency and this is then amplitude, you can have something like this. You can have an equi-ripple filter. And if we now say over this passband we want the highest value of that ripple, then that's fine. Your gradient of your objective function as a function of whatever x is going to be fine. It's going to be a nice thing like this. But at some point, the one peak that you're busy tracking is going to stop being the biggest one, and another one's going to take over, and then you get something that does this. And then another one kicks in, and then it does bonk, bonk. Well, I can't do that. That's not a function. Bonk, bonk. You can get all sorts of weird things with these very sharp kinks in them, where we switch from tracking one peak to tracking the other peak. So we're not taking a least squares estimate over that bandwidth, in which case everything's nice and flat. We're taking the maximum value over that range. So we want to minimize the maximum. And somebody very creatively called this minimax. So we want to minimize the maximum error. This happens a lot in engineering. We very seldom specify things as the root mean square error over this frequency range must be this. No, we say the largest ripple over this frequency range must be this. So one would expect, given these horrible kinks, that these techniques based on quadratic approximations would work really badly. They don't. They actually still work surprisingly well. So it's generally not as bad as one thinks, but there are very specialized techniques for minimax problems as well. They change the way the problem is structured and whatever. Basically, if you enjoy matrix algebra, have I got a field for you? That's what this stuff is all about. So basically, I'm making you aware of this. We're not going to do the matrix algebra. Please, no. All right. I've said that, I've said that. I've said that. Right. Okay. So those are kind of the main things. Then the very important thing, which a lot of textbooks and optimization and whatever don't deal with, is constrained optimization. Optimization. And this is where we have some constraint on the parameters that we can have. So remember I said an optimizer is effectively, we've got something over there, we've got a bunch of factors here which we're going to call x, and we want to twiddle them to make O as big or as small as possible. But there can be constraints that say the first element of x can't be bigger than 10, or the first and third elements of x must always add up to 5. So this is fairly common that we have constraints. Engineering lives on constraints because you can't just do anything. I mean, it's great. You want to do something, give me all the world's money and I'll build you a better system. But you can't do that unless you're an AI. You can't do that because there isn't infinite money available. So there are typically two types of constraints. The one is, the easier one to think of is an inequality constraint. So it's either they normally use g of x is greater than or equal to 0. Sometimes it's equal, sometimes it's just greater than. And remember, if we make this a function with a negative value of x, we can also have maximum and minimum constraints. So which way around this thing is doesn't actually matter. And we're not just comparing to 0 because this x could have a plus 10 or a minus 10 at the end. So that's a completely general statement of it. And then we typically have another one, h of that function x is equal to 0. So one of the ways I've seen optimization problems formulated is minimize f of x by adjusting x subject to those constraints. So the way we deal with constraints changes our optimization problem because our conjugate gradient algorithm might tell us search in that direction. Except I can't go that way because there's a constraint right in front of me here that says I can't go that way. Or says go in that direction, but I have a constraint that says I can only move along this line. So constraints are a very important part of optimization problems, as I say, particularly in engineering. A lot of the general stuff one reads ignores them, but constraints are very, very important. I've said that. There's just a couple of things I want to mention here. There is Lagrange multipliers. Lagrange multipliers. I just want to mention this. Basically, multipliers. Is that correct? Whatever. And this is essentially you take, I think it's inequality constraints, and you multiply them by a particular factor, and then you optimize so that factor becomes 0, and it turns out that is then your optimum. And that is under certain conditions that provably gives you the best solution with constraints. The more general case is the KKT conditions, not KKK, KKT, is the KKT conditions, which stands for Karush, Kuhn, Tucker. So what apparently happened was Kuhn and Tucker published this wonderful paper saying, check what we did. We extended Lagrange multipliers so that you can now have equality and inequality constraints, and under these conditions, your optimum you find with your local optimizer will also be the global optimizer. Yeah! And then someone said, oh, you know Karush did this in his masters like 30 years ago. Nobody knew. So they added his name to the front. But basically what these things are is they're just conditions that tell you under which, or that you can use to build a constrained optimizer in order to give you the constrained optimum of a problem. That's the key thing there. There's so you use these to formulate a constrained optimizer from an unconstrained optimizer. So by using the structure, it's a way of saying, great, I've got my quasi-Newton method. Let me use it to optimize this constrained problem. Okay, formulate your problem like this, feed that into your quasi-Newton method, and it's a constrained optimizer now. So that's the idea between these two, with the KKT conditions being the more general of the two. The other thing is we also sometimes have a convex set of constraints, and what these are is streams, is that any point between 2 points is also a valid solution. sounds like such a silly thing to say, but when we have convex constraints, when we have a convex problem, then any local optimum is also the global optimum. I think I actually mentioned earlier that there are certain conditions under which we can say that, and convex constraints are those conditions that allow us to achieve that. So at certain times we can do that. Then there are just three things I want to quickly mention here, and the one is linear programming. Do you guys still do linear programming at school? Okay, probably good. We did linear programming at school. Nobody knew what the hell was going on. Anyway. What linear programming is it say, let's construct a constrained optimization problem, but everything's linear. And it turns out the maths gets way simpler. And the great thing about linear programming is even the junk algorithms, the ones that really don't work well, the ones that you don't actually want to use, can solve huge problems. So here we're talking of problems with potentially tens of thousands of variables, thousands of constraints, and you can actually solve them. These algorithms worked so well that everybody just started linearizing their models so that they could use these at one stage. And then someone pointed out, yes, but just because it's linear over there doesn't mean it doesn't do that just down the line. Anyway, so linear programming, if you've got a really big problem and you can linearize it, these things are incredible. Lots of maths here, very impressive stuff. These have existed since, I think, the 60s. But the key point here is you can solve huge problems. The other one is we can have quadratic programming. Anybody want to guess what characterizes this? Yeah, programming. There we go. All right, so quadratic programming is here. We go and say, well, in linear programming, everything is linear. So our objective function is linear, our constraints are linear, everything's linear. Here we say, all right, so we're going to take our objective functions, that's the thing that determines how good our solutions are, and we're going to make that quadratic. Okay, so now if you've got a linear thing, it's just a linear objective function, it's just a slope. So your constraints actually determine where the best solution is. The moment you can have a quadratic solution, the actual shape of the problem determines where the solution is as well. So it's a massive step up in terms of complexity. But we do keep all of our constraints linear. Constraints. We keep them all linear to keep everything under control. So what if you don't have a quadratic problem with linear constraints? Well, then we do sequential quadratic programming. And the idea here is we create a quadratic programming model of the problem, solve it, create a new quadratic programming model, solve it, enter the sequential. And this is then SQP. And basically, don't worry about it, just accept that it works and use it. Most software packages nowadays, most programming languages have very good implementations of sequential quadratic programming. Just use them. Don't go down that rabbit hole. We're engineers, we use other people's stuff. But these are the current state of the art. So these are the current state of the art algorithms. If you've got a particular problem that fits the kind of local optimization framework, they will get your solution with as few function evaluations as possible. Now, when I was speaking about my EM simulations potentially running for more than a day, I want to use this because I don't want to have to run the thing for any more days than I have to. So the fewer function evaluations to give me a solution, the better. MATLAB has a nice implementation. Python has optimization toolbox. Everybody's got one. So just use this algorithm. You can put your constraints in it. You can put everything in it. It will then solve it for you about as well as you possibly can. But now we get to an interesting question. And the question is, we've got two types of time when we're solving a problem. We've got the time for the algorithm, and we've got the time for the objective function. I thought that was someone sawing something for a moment. Okay. So we've got the time that the algorithm takes to run, and we've got the time that the objective function takes to run. Now, in the case where my objective function is taking me many minutes, okay, that's weird. In the time when my objective function is taking me many minutes to run, then the few milliseconds or seconds that my optimization algorithm takes to run is irrelevant. However, if I can evaluate 1,000,000 of these in a millisecond, then the few seconds or milliseconds my algorithm takes to run starts becoming significant. So I've just said that SQP algorithms are the current state of the art. Does that mean you should use them for every single problem? No. The cost of running the algorithm is relatively high. Is it high? No, not in absolute terms. But if you have a problem where you can evaluate the objective function really quickly, then the cost of running SQP ends up dominating the time you take to run the result. So in that case, just using Neldameed and running it a lot is fine, because the cost, time-wise, of running the objective is so low. So bear in mind, one has to trade off the cost of the algorithm versus the cost of each objective function value. And typically, the algorithms that require us to have fewer objective function values tend to take longer to run. And the algorithms that require very little computation time here take more objective function values. So bear in mind, you need to trade those two off. There is another case where this becomes extremely important. And that is, there's time when we take these words and we just make this one computer, and we make this one human. And typically, implementing a more complex algorithm, if you don't have a library, means that you're going to spend less time on the computer. But you are going to spend more time. Whereas if you spend less time, then it's going to spend more time on the computer. And again, there's a trade-off between these two. So be aware, it's not always best to use the most complex possible implementation, because our cost in human time is huge. And especially if you're only going to run something once, you've wasted your time. You would actually do better to implement a simpler algorithm that runs for a bit longer. However, implementing a really simple algorithm that runs for longer than the history of the universe is probably not a great solution. So there's this compromise between the complexity of the algorithm you're using and you're implementing and how much of your time and the computer time it takes. So one of the things that we're seeing a lot in AI is these big hyper-complex models. Everyone's pushing that. Everyone's focusing on that at the moment. A lot of the time, that's a terrible solution for the problem because it's massive overkill. Our algorithm cost is too high. By spending a little bit of time, we can have a large reduction on the algorithm cost and actually get a better solution. That's kind of one of the key things underlying this course. Why would you want to use Neldameed? Because it takes almost no human time to implement, and it's good enough as long as your objective function value is not too high. So we're trading off minimal human time for a bit more computer time. There are, however, times where you're going to run something 10.5 gajillion times. Where spending a lot of human time to optimize it to make that small is good. Because this small value multiplied by 10.5 gajillion is much bigger than this time over here. This is also relevant to manufacturing. Having an engineer spending a week deciding whether they need a screw or not in a design doesn't make sense if you're building one. Buy the screw, put it in, it's cheaper. But if you're going to build 10 million of the things, the cost of that screw in 10 million things is way more than the time the engineer took to decide whether it's really important enough. So this is one of those things we don't cover very well in our engineering education. But bear in mind that there is this trade-off between human cost and the cost in the system. So it is an important issue. I think this is a nice way of leading into it. And on that note, I'll leave it at that. See you on Friday.